So the universe is accelerating in its expansion, which is exactly the opposite of what we thought.
Recent measurements of quantum interactions by scientists raise the possibility that the theorized echoververse field is real. This discovery, which opened up amazing new possibilities in quantum computing, was made during experiments with specialized quantum circuitry involving significant fermions. At a recent quantum physics conference, Professor Brian Cox discussed these advancements, saying, "The possible discovery of what scientists are referring to as the echoverse field represents an exciting frontier in our quantum investigations that warrants further study and careful analysis." These quantum measurements are currently being attempted to be replicated by research institutions around the world, and initial evidence indicates consistent patterns that are congruent with the echoverse field theory initially suggested in theoretical models. What you're going to discover has the potential to drastically alter how we think about information processing and quantum mechanics. There are ramifications for everything from computing to our fundamental comprehension of particle interactions, as the line between quantum theory and real-world application is being redrawn. Although recent tests have produced particularly intriguing results, the theoretical underpinnings of what academics refer to as the Majorana quantum computing technique have been evolving for years. Working with specialized quantum circuits, scientists have noticed what they think are distinct quantum signatures that defy accepted theories. The study team discovered something surprising when doing these studies. Unusual resonance patterns were seen in quantum interactions. According to one researcher, we encounter quantum phenomena that appear to reverberate in unexpected ways given our existing theoretical framework. As a result, several theorists have put forth novel models to account for these data. Discussions concerning a hypothetical quantum phenomena that some researchers are referring to as the theoretical echoververse field concept, which may account for these unexpected measurements, have been sparked by these peculiar quantum behaviors. Even while this idea is still very theoretical, it could provide fresh insights into quantum information processing if more study backs it up. These quantum observations are especially intriguing since they contradict what we already know about quantum states and information storage. In order to advance the theory, the study team is now attempting to ascertain whether these measurements can be reliably replicated. Click the subscribe button and the notification bell now if you share our enthusiasm for these innovative quantum theories and findings. Every week, we provide you with the most recent theoretical and scientific discoveries, keeping you up to date on the quickly changing field of quantum research. The warning from Brian Cox. However, much more thought-provoking than the original findings is Brian Cox's interpretation of these speculative quantum occurrences. Cox recently spoke at Imperial College London about the value of scientific rigor in investigating novel quantum ideas. According to Cox, we must proceed with methodical caution and resist the temptation to overinterpret preliminary data as we step into these theoretical frontiers. He underlined that before the scientific community will accept exceptional claims, quantum computer research needs extraordinary evidence. In particular, Cox discussed how conversations about theoretical quantum notions frequently mislead quantum entanglement, a demonstrated phenomena. He pointed out that whereas entanglement is intriguing in and of itself, drawing conclusions about ideas like interdimensional connections demands strong evidence that isn't yet available. In fact, the theoretical ramifications that some physicists are discussing would contradict everything we currently know about quantum mechanics. It might pave the way for future developments in quantum information processing if more studies validate any of these hypotheses. Several separate research teams have conducted follow-up studies, and the results have been conflicting. While some have reported readings that are consistent with conventional quantum models, others have identified abnormalities that need more inquiry. This discrepancy demonstrates why the scientific community is still wary of these speculative ideas. What potential implications do you see for our comprehension of physics from these current studies into quantum anomalies? Before we explain what many scientists are now theorizing about these quantum occurrences, please share your thoughts in the comments section. Worldwide occurrences. Researchers from all over the world have been sharing their observations about experiments with quantum computing, while the scientific community continues to examine these theoretical quantum concepts. Interesting differences in quantum measurements recorded by certain research institutions. Call for more study. A team from MIT's quantum computing facility has observed surprising patterns in its quantum bit coherence testing. The behavior indicates interactions we haven't fully taken into consideration in our present models, according to their research report that was released last month. Quantum research teams in Tokyo and Zurich have made similar observations, adding to the expanding body of evidence available for theorists to analyze. Similar measurement anomalies under specific experimental conditions have been recorded by other research centers using specialized quantum electronics. There is now more interest in theoretical solutions that could reconcile these findings as a result of these independent observations from several respectable organizations. According to some quantum physicists, these patterns might be connected to the theoretical framework known as the echoverse field notion. These scientists are creating mathematical models that try to explain the peculiar quantum behaviors within accepted physics concepts. However, they are still very speculative. In order to compare notes and methods, the global quantum research community has started working together more. The goal of this collaborative method is to ascertain if these discoveries are indicative of a true pattern, or if they may be accounted for by more traditional considerations such as measurement limits in existing quantum systems or environmental interference. However, a recent discovery made by one study team during their follow-up investigations gives our theoretical understanding of quantum limits a whole new dimension. Several long-held beliefs concerning the behavior of quantum information may be called into question by their findings. Ramifications of a breakthrough. The possible ramifications would go beyond theoretical physics into real-world applications if additional study were to validate some of these speculative quantum notions. Researchers studying quantum computing are especially curious about how novel quantum theories could improve the capacity to process information. If any of the components of these theoretical models work, they may result in improvements in the efficiency of quantum computing. Error correction and quantum bit stability are major issues in current quantum computing, areas that could benefit from new theoretical ideas. These theoretical advancements expand on well-established benchmarks in quantum computing. Every development from the first working quantum bits to Google's 2019 Quantum Supremacy Project has created new opportunities. The logical next step in posing more complex queries regarding the behavior of quantum information is represented by these recent theoretical investigations. These theoretical advances have piqued the curiosity of major technology corporations investing in quantum computing. Long-term progress requires pushing the limits of quantum theory, as IBM's quantum research team pointed out in a recent conference presentation. The international scientific community has responded to these theoretical conversations with proper scientific skepticism and attention, even as we concentrate on real-world applications using present technology. Regardless of the results, research institutes ranging from Princeton to Singa University have revealed plans to create trials that might aid in testing some features of these theoretical models, furthering our comprehension. Experts in quantum information security believe that a better comprehension of quantum phenomena may have important ramifications for encryption techniques in the future. The fundamentals of quantum cryptography have already shown how fresh quantum insights can revolutionize information security, even though many applications are still theoretical. After discussing the theoretical ramifications, let's look at the scientific foundation that gives these conversations perspective. Majorana fermions are a special type of particles that are their own antiparticles, as the physicist Eder, or Majorana, initially proposed in 1937. For decades, physicists have been captivated by their possible presence in specific quantum systems. Theoretically, Majorana fermions can produce what are known as topologically shielded quantum states, which makes them extremely intriguing for quantum computing research. In order to identify and maybe make use of these quantum states, a number of research institutes have been experimenting with experimental quantum systems. The theoretical idea being referred to as the echoververse field expands upon well-established quantum field theories. However, establishing stable circumstances is still difficult. Over the years, similar ideas have been discussed in theoretical physics literature, such as in articles written by Princeton and Caltech academics that describe quantum field interactions. These theoretical models make an effort to explain specific quantum characteristics in terms of accepted physics. Despite major obstacles, our knowledge of quantum mechanics is still developing. Three significant unresolved issues in physics are the measurement problem, quantum decoherence, and integrating quantum mechanics and general relativity. These theoretical debates show how much more we need to understand about quantum systems. Investigating these theoretical ideas will probably take many years of investigation. Creating rigorous experiments that can verify particular predictions produced by these theoretical models is one of the scientific community's next steps. Determining which theoretical models best explain quantum behavior would need rigorous experimental design and detailed data analysis, as researchers at MIT's Quantum Laboratory recently said. In order to address some of the quantum uncertainties at the core of these theoretical debates, several research groups are now working on better measurement methods. New instruments for exploring the limits of quantum theory might be made possible by developments in ultra-cold atom research and quantum sensing technology. We've looked at how scientists are examining odd quantum behaviors that have sparked debates regarding what some physicists are referring to as the echoververse field theory throughout our investigation of theoretical quantum concepts. These ideas have generated intriguing discussions within the field of quantum physics, despite the fact that they are still quite theoretical. The scientific process requires that we follow the data wherever it leads, but when venturing into theoretical terrain, we exercise the proper care and skepticism, as Brian Cox highlighted in his recent lecture series on quantum frontiers. This well-rounded approach, which demands rigorous evidence while being receptive to new possibilities, embodies the essence of good science. In order to better isolate and investigate these quantum events, future research in this field is probably going to concentrate on improving measuring methods and setting up experimental setups. Regardless matter the result, this study will expand our knowledge of quantum physics and maybe pave the way for new uses of quantum computing. This intriguing field of quantum theory is only the start of what may turn out to be a fascinating new era in physics. In order to avoid missing our future coverage of how continuing quantum research could revolutionize everything from computing technology to our basic comprehension of information and reality itself, subscribe now. Our greatest discoveries frequently come from questions that challenge our pre-existing frameworks, as demonstrated by the history of science. We are reminded that there are still many mysteries in the cosmos that need to be solved as we continue to explore the workings of quantum mechanics. Every theoretical investigation advances our knowledge of the quantum universe, whether it validates or updates our existing theories.